Today we have one of those wonderful colloquia where you can invite somebody back to the IOA. Stefano Facchini did his PhD here at the IOA and then did a postdoc at MPE and then a fellowship at ESO. At the moment, he's an associate professor at the University of Milan and where he leads the ERC project Unveils. And today he'll be telling us about that, I believe, right, in planet-forming environments. Thank you very much.
Thank you. Can you hear me okay with the microphone on? Great. So first of all, I'd like to say that I'm extremely thankful for the invitation because this gives me the opportunity to be back here. And you know, as your career progresses, it's very moving to come back to the place where you actually graduated and be thankful to all the people who contributed to that achievement. So again, thank you for the invitation very much. And before getting into the science, what I would like to do from the beginning is to acknowledge a tremendous contribution for a large group of collaborators, in particular the members of the exoALMA team, which I'll explain in detail today, who did a tremendous amount of work in the last 3 years to get to some of the initial results that I will show today and discuss in this colloquium. And among them, I would like to thank in particular the work of a few PhD students. You see them happily here. That means that the group was a success. Students were happy, who did most of the heavy lifting of this large program that I'll discuss today. And many of them are postdocs now, since this project has been longer than we hoped. And one of them is actually in the audience, Cristiano's here. But let's get into the science. So I'm sure that we're all very much aware that our perception of the universe, of our starry night, changed dramatically as humankind once we realize how densely populated our galaxy, and therefore by extrapolation the universe is, of exoplanets. And on average, we think that each star, at least in our solar neighborhood, hosts at least one planet around it. And once we started collecting the data, one of the results that came out is not only the extremely high efficiency of planet formation, at least on a stellar by stellar basis, but also on the extreme diversity that these exoplanetary systems exhibit, both in their physical properties, their mass, radius, orbital distance, but also in their chemical properties, both in the interior and the atmosphere, that we can now probe, for example, with spectroscopy, with several instruments, including JWST. So one of the goals of the research, or the research community I'm part of, is to try to understand how is this diversity and this high efficiency come to be. Because in the evolution of planetary systems, some diversity can indeed occur and be sculpted into the systems, but the diversity of exoplanetary systems must be sculpted, at least at some important level, in the conditions, or for the condition in which these planets were born, and the environments in which these planets were born. These environments, which are very well known nowadays, are called protoplanetary disks. And here I'm showing a gallery of them as seen with extremely high angular resolution ALMA observation at millimeter wavelength in their continuum. So we're seeing at pebbles that are about 1 millimeter in size with high angular resolution for the largest disks we have in the sky. And we see that we have these clear substructures, and the predominant one is this structured rings and gaps in concentric morphology. So to make a long story short, several people, or the majority of people in the community, think that at least some of these substructures may be due to planets that we still need to identify. So if this is the case, this suggests that we have an indication of yet unseen protoplanet population that is shepherding the dust particles of their natal environments. And if we try to populate the same plot as before by the planet masses and orbital distances that we need by forward modeling the morphology of these systems, this is the population we get. And I'll come back to this at the end of the talk. As you can see, it's a quite different population from the exoplanetary systems we can usually detect, and that's mostly due to observational biases. It's not a real effect, we believe. Today, I would like to focus mostly on this upper right part of the plot, again, because that's what we can do in terms of observations. These are the systems for which we can really try to characterize the formation environment and for which we can characterize the planet-disk interaction in disks. These protoplanets need to be massive and need to be at fairly large distances in order to see them interacting with the disk with spatially resolved observations. But to try to make a list of a few key open questions that are very much open in the community, even after decades of research in the field. Let's start from actually the bottom one, is what are the main physical and chemical properties of planet hosting environments? And with properties, I'm talking about even very simple properties. What is their mass? What is their surface density? What are the turbulence levels? What is the chemistry that we see in disks inherited from the protostellar stage, or is it reset completely? And other questions such as where are the planets that may be sculpting the disk density structure? What is their formation pathway? Are they so-called hot start, retaining a lot of the entropy they get as they accrete, or are they cold start? And finally, what are the main physical and chemical, potentially, processes that do promote planet formation in disks? While a lot of theoretical development has thankfully happened on this, we still lack an observational characterization to answer many of these questions from an observational perspective, and that's where my talk will try to kick in. It's really an observational talk. So talking about observation, most of the, if not all of the observations I'll show are, this seems to be a bit low resolution, but you'll recognize the ALMA interferometer. This interferometer operating at millimeter and sub-millimeter wavelengths in the Chalantor altiplane in Chile at 5,000 meter altitude. And again, it acts as an interferometer to get very high angular resolution by using very extended baselines. So let's have a look at protoplanetary disks. These are mostly done by these planet formation environments. These are mostly done by dust at 1% level. And if we look instead at their gas counterpart that contains about 99% of the mass, they look radially more extended. It's mostly an optical depth effect. It doesn't mean it needs to be a surface density effect. And if we get these images of the gas, this in particular is the integrated intensity image of a CO rotational line, the 2-to-1. What it means is that underlying we have, or we can, as we'll see in a bit, extract a velocity map of the same gas. For example, as this one here, where we're able to map at a very high precision the projected velocity map of these rotating structures. So how do we get there? We will see it. But what I would like to highlight that very often we are used to see this kind of data, but the underlying data are way richer in terms of their information. Because the actual data we get are what we call data cubes. And data cubes effectively are mapping the intensity of a given, in this case, molecular line for a given velocity band. So as we go through these, the velocity beams we have, what we are effectively tracing is the shape of the isovelocity contours. And that's exactly what we're seeing here, this typical, what we call butterfly pattern. And what this means is that we have a lot of information in this kind of data about the dynamics and the velocity structure of disks. Why is this important to us to try to tackle some of the questions that I listed earlier? Well, that's because the protoplanetary disks are extremely dynamic, extremely complex in terms of their dynamics. And the gas dynamics is what's driving most of the physical mechanisms that are occurring in protoplanetary disks. Just to list some of them, we must have turbulent motions on eddies of different scales. We think we have magneto-hydrodynamical instabilities that can promote or hinder planet formation. Kinematics can be used to trace planet-disk interaction, which also make planets accrete and migrate throughout the disk. We can have winds, which may drive the evolution of disks. We can then have tidal interaction with, for example, other stellar companions inducing warps or flybys. And in general, we expect to have coherent large-scale gas flows in disks. How do we assess all these physical mechanisms observationally? So what we do is we leverage the line data cubes we get for spatially resolved information. So if we have a data cube and we decompose it in different velocities, this means that in each pixel, effectively, we have a spectrum. The spectrum is associated to three main quantities. We have a line centroid, which is mapping or which is associated to the bulk gas motions. We see how the gas is moving coherently. We have a peak intensity, which is usually related or must be related at some level with the temperature if we're optically thick, or column densities in case the line is optically thin. And then we have the width of the line, which can be informative about thermal, collisional even, and turbulent motions in these systems. So if we focus on one of these channels, for example, this one, you can see that the emission actually branches out in two different layers. And that's because we have an upper surface of the disk where CO, in this case, is emitting from. CO is frozen out in the disk midplane. And then we see the CO back again from the bottom side of the disk in two distinct conical shapes. And that's why the disk is branching out in these layers. Without going into the detail of how we do this technically, but what we can do from these channel maps is we are able to reconstruct the 3D surface of the emitting layer of this emission, both from the front side and the back side of the disk. And this will be crucially important to derive accurate temperature estimates of this, as I'll show later. But it's also crucially important if we want to accurately deproject each data point and associate it to a 3D point where we want to associate each point to a given velocity. So if we know the 3D structure of the emission layer, what can we do? So first of all, we can try to decompose the velocity field in the three different vectorial components. If we assume that we are azimutally symmetric, that's a big assumption that you should always keep in mind, then it is possible to reconstruct from the projected velocity, which is what we see, it is possible to extract the rotational component of the vector field, the radial component, and the vertical component, plus some systemic velocity. And we can do that because it's an orthogonal basis, and so the three of them are independent, and the solutions are not heavily degenerate. And with the current level of data, we can do this at a precision that it's about 10 meters per second. This is a precision, not an accuracy. We'll see the systematics play a role. But if you think about the kind of accuracy we can reach, I think it's mind-blowing for, at least as I've seen the field evolving, it's still mind-blowing to see this number written there. So in this talk today, I will not talk about radial and vertical motions, but I will mostly focus on rotational ones, which is dominated by, as we'll see, Keplerian rotation, as I show here. So if we focus now on the azimuthal component of the velocity field in a disk, This is driven mostly, can be described mostly with three factors. We have a Keplerian term, which is dominated by stellar gravity, of course. Then we have the pressure support, since we have a collisional fluid. We're not using stars. And then we have a self-gravity term. So while stellar gravity dominates, so the disks are almost Keplerian, we now have the precision to try to measure pressure gradients, so the second term, as we will see self-gravity of disks in a few cases, as you see from this last term. So in terms of data analysis I'll use today, I use two main methodologies. One is rotation curves of this protoplanetary disk. This is one extracted from the data of a particularly bright extended disk. And this can be used to infer the pressure structure of disks, try to get estimates of the stellar, the central mass of the star, the mass of the disk, and if possible, even how the disk is truncated exponentially in the outer regions, because that will leave a strong imprint in the pressure profile. The second methodology I will be using is kind of different. So what we do is we take the field, the map of the velocity centroid of our data, and then we subtract usually a Keplerian model, a purely Keplerian model to the data, accounting for the 3D geometry of the emission. And then we study the residual maps, because these residual maps are what could reveal basically waves that are propagated in the disk and could reveal important physical mechanisms such as vortices, planets being embedded in disks, instabilities like gravitational instability, as we heard yesterday, or other mechanisms. So let's go back to the questions I listed earlier. So I'll try to tackle some of them in any way. I will not be conclusive in any way, of course. What I will not do, just for sake of time, is chemistry, which I try to have, but let's remove it. I will not talk about it in the colloquium. And what I will not talk about, because that will require quite some time to be very precise about what's going on in the field, is turbulence. But if you're interested, we can discuss. So how are we trying to tackle it now? This is not a review, so we'll not talk about what's been done in the field in the last 3 years or so. But what we'll discuss today is the results of this ALMA large program that we proposed for, I think, 3 years ago. So in 2021, which is 180 hours of ALMA time to try to characterize the disk dynamics of 15 protoplanetary disks. What's new compared to other ALMA large programs that happened in the past? Well, first of all, is that we go much deeper. We have more than, let's say, 10 hours per source. We go at 0.1 arc-second resolution, roughly speaking, and we push the spectral resolution to roughly 28 meters per second. So we have channel spacing of 15 kilohertz at the correlator level. This is done in band 7 because it's for ALMA experts, so at about 350 gigahertz, because it's actually way more effective than band 6 when you want to trace optically thick tracers like CO. A factor of 3 more efficient in terms of on-source time. The 3 main lines we target are 12 CO322, 13 CO322, and CS 726. Why did we pick these 3 lines? The first 2 is because 12 CO is the brightest line we have. So if we want to have high signal to noise to trace the dynamics, that's the first line we want to have in your spectral setup. The second line is because it's slightly optically thinner, and therefore you're probing lower emission layers in the disk. And we included CS because it has a higher molecular weight, and if you want to try to infer turbulence, you expect the thermal width of CS to be narrower, and therefore to be able to discern and distinguish turbulent motions from thermal broadening using heavier molecules. So, and the goals of the program is really to make again, a long story short, is really to probe the dynamics of these protoplanetary disks. Just to get a quick idea, but I'll show many images of the level of the data for people who are used to this. The field, this is the channel maps this is 100 meter per second resolution. This is the V4046 SAG disk. And this looks like a radiative transfer model to me. The data quality is astonishing compared to what I'd always worked with before. And again, this is about 100 millisecond resolution. So let's first have a look at the continuum, because that also tells us how we selected the sample. These are the continuum images of the 15 disks. As you can see, many of them have a large cavity in the middle. That was somehow not intentional, but it came out because the selection that we used to the criteria we used to select the sample were very simple. We wanted the largest disks in the sky to have as many resolution elements as possible to be able to trace the dynamics properly. And you need resolution to do that. And most of the very large disks in the sky are what we call transition disks, so disks hosting a large cavity in the middle. As you can see, then we have a large variety of these. Some are very azimuthally symmetric, like this one here, LK calcium 15. Some are very asymmetrical, like MWC 758, this one in the bottom left. So the first thing we did, just spend a few words on what we did on the continuum, is we tried to extract the symmetric part of the continuum emission using some modeling in the visibility space. And after removing the symmetric part of the continuum, you're left with some residuals, which gives you a measure of how asymmetric disks can be. Asymmetries can occur for different reasons. For example, this one is actually due to shadows, creating temperature azimuthal structure in disks. But to summarize the results of this analysis is that we managed to parameterize a non-axisymmetry factor, so a mathematical way to tell you how asymmetric these disks are in their continuum emission, and to try to see if it correlated with other parameters, for example, accretion rate here on the left, or near-infrared excess here on the right plot. What stands out pretty clearly is that the most asymmetric disks are clearly correlated with high near-infrared excess. And the other result is that even if the sample is small, is that you do not have low accretion rates for asymmetric disks. And this is telling us that there must be a relation between the large-scale morphology or dynamical state of disks and whatever happens in the very inner regions, which is what the near-infrared excess is tracing, or what the mass accretion rate is tracing. But this talk will be mostly about gas, so let's move to it. These are the images of the peak intensity of the 12CO. So it's effectively tracing the peak brightness temperature, or the kinetic temperature, if it's when we're optically thick. And we see different morphologies in these objects. We see some of them which host clear spiral patterns like here. Some show shadows like this one. And here we have another spiral. Let me rotate a few of them for you. We see again some spirals. We see shadows in a few cases. And in other cases, we have this annular corrugation in how the CO emits. So what do we do with the data? First of all, we use an amazing analysis package that was developed by Andres Izquierdo, who's now Hubble Fellow in Florida, which supports anyone who wants to play with line data to get a line tomography analysis of the disks. So here, for example, I'm showing the fitting of the spectrum along this annulus. As you can see how we're able to fit properly the back and front side components. And by using this package, the first thing you're able to is to get the emission layer of these disks. Here I'm showing for a subsample, because I'm not including, actually they're all of them, there are 15, I believe. What we're showing here is the emission layer of 12CO. Here you see in black the data points that you need for the day projection, and with different lines are different parametric fits, or let's say parametric representation of the surfaces. Why is it crucial again? We need it for the projecting the velocity field properly, but the second thing is that we needed to have an empirical estimate of the temperature of the disks. Why? How can we do that? If you have the emission layer of 12CO, let's pick this alkyl calcium 15 disk, then you have the emission layer of 13CO, and both of them are associated to a brightness temperature. The lines are optically thick, that's equal to the kinetic temperature. Now you're probing different temperature structure, different temperature measurements at different layers in the disk. And with a parametric fitting, you can try to reconstruct the whole temperature structure of the disk, extrapolating all the way down to the midplane, where we have some constraints from the continuum. And an enormous effort in the team has been to try to derive reliable uncertainties with this methodology, including the systematics we have, which are actually significantly large, as I may get to later. And so the first point is that we're able to get the temperature structures, and we'll need them. The second thing we did is to try to get the pressure structure of these disks. How did we do it? Is by neglecting this self-gravity term. If we are able to get the Keplerian term, which is the dominating one, which is fairly easy, what then we can get is this basically dp by dr as a function of radius. And that's what we have here. This is for the different lines, so 12CO and 13CO. This is the logarithmic derivative of the pressure extrapolated down to the nearest midplane from where we computed in the emission layers. What we want to check is how pressure modulations may affect the dust distributions that we saw in the initial plots. So we try to play with the first derivatives of this, but it didn't work immediately. So what we did is we used second derivatives of the delta V phi, which is the how the velocities are mismatched compared to the underlying Keplerian rotation. So roughly speaking, a negative derivative, so a negative second derivative is can be correlated to a pressure maximum, whereas a positive, second derivative correlates to a pressure minimum. So we counted how many dust rings correspond to negative ones, so to pressure maxima, and that's more than 60%. And then we counted how many gaps correspond to pressure minima, and that's more than 75%. And for the 40 and 25%, I'm not including here, is we're actually limited mostly by resolution. What this is suggesting is that pressure modulations is what generating the dust substructures we saw in the first ALMA images. This is something that has been predicted. People probably gave it for granted, but here we have observational evidence that pressure is driving radial drift of this dust particle and concentrating them in annular rings. What we did then is to compute how different layers rotate at different velocities. For one disk, we also had C18O. So what we did is we computed the difference in velocities between 12CO and C18O, just squared, because it helps with comparison with theoretical models. So if you were to assume that the disk is vertically isothermal, the difference in velocity would be this green line here. But if you do consider that the disk is vertically stratified, as we did characterize, as I showed 3 slides ago, then you get this purple line here. And this is where the data lie. So what we're seeing is that we can now measure the vertical shear of the rotation, which is directly related to the 2D pressure structure of disks, where you have both the vertical component of the pressure gradient and the vertical, both the radial and the vertical component of the pressure gradient. So what this is telling us is that kinematics now is giving us a way to probe the 2D pressure structure of disks. I will not focus on these wiggles because that's telling us that there is substructure in the pressure modulations, which I'm not considering in this fitting. So let's make another step in how we use rotation curves. And let's focus on this last term here. If we manage to have a good idea of what's happening in terms of the Keplerian rotation and the pressure structure in disks, what we can try to do is to infer the dynamical mass of the disk itself by looking at its self-gravity part. So how do we do it? Differently from the pressure structure where we can do it non-parametrically, we need to use a parametric fit to fit the whole rotation curve with these 3 different terms. And if we do it, we get that in, I believe, 6 disks of the whole exoALMA sample, we're able to infer a disk mass that is robustly above 0. It's above 5% or more of the stellar mass. And here representing the parametric fit of the surface density simply, it's basically 1 over that, by showing the Kummer parameter for the disks. So we have evidence that these disks are gravitationally stable. I will not go, unless maybe later if there are questions about the systematics that we can get by the fact that we do use a parametric fit for the surface density. So we're not doing it non-parametrically yet. How can we benchmark if this method is correct? How else can we measure masses? There is one way to do it, which is very new, I think, and that's using collisional broadening. This was work done before exoALMA by Tomohiro Yoshida, PhD student in Japan, who looked at the spectrum of the very inner regions of the 12CO of a protoplanetary disk. And what you can see in this log linear plot is that you have these huge tails in the line wings. And these huge tails are not Gaussian, but they're Lorentzian. And as you know from your radiative processes class, that means that you must have a collisional term in your line width broadening. And that's exactly what's happening here. But what we can do then is to try to do the same on one of the exoALMA sources where the data now are better than what Tomohiro had at the time. And to do so, we pick one face-on disk. That's because since we are going very deep in the line wings at low signal-to-noise ratio, we do not want to deal with radiative transfer effects that would arise as soon as you start inclining the 3D structure of the disk. So what we do, here you're seeing on the x-axis you have the velocity, on the y-axis you have the radius of the disk, and in color code you have the azimuthally stacked spectrum of the disk. So each line here would be a spectrum at different radial location throughout the disk. If I saturate the color scale, you see that at this location, this radial location, which is exactly where you have your dust ring, you see that you start seeing these kind of tails. If I take this annular range, which I highlight here with the 2 horizontal lines, and I plot them, I average and I show it in this left side plot, you see that the tail is still Lorentzian, it's not Gaussian. And that's something we can also model introducing some turbulent motion. collisional broadening. Why is this extremely powerful? It hasn't been used much in the community. That's because we didn't have the data quality to do it. But it's collisional broadening gives you a direct measure of the density of the collisional partner of CO. And in this case, it's H2. So what we're measuring is not a surface density. We're measuring the volume density of H2 along the emission layer of CO. So with some modeling for the disk, we can try to infer the surface density of the disk and non-parametrically, which is what we get here in blue. And it turns out that this matches extremely well the pressure structure we're getting from the rotation curve. So the two methods work very well. And again, I will not spend more time on this one because I'm going extremely slow. But this is to say that this is a new methodology for which we can benchmark our mass estimates in a few protoplanetary disks. So, but what about methods that were usually used to infer masses in planet-forming environments? Here it's a collection done by Anna Miotello in her PP7 chapter, where you see measurements of the disk mass of the most studied disks to date. And you can see that the masses vary by almost 2 orders of magnitude. That's because typical methods to estimate disk masses are hugely uncertain. If you're using continuous emission because you don't know the optical depth, and because we don't know the opacities. If you're using CO, it's because we do not know if CO is underabundant, if there is a chemical process that is sequestering carbon from the gas phase. There is a promising way, which is HD, but we're lacking far infrared emission so far. Let's see what happens with the new NASA probes between the X-ray and the far infrared one. And then there is a final method that has been developed in the last couple of years, which is measuring these masses by measuring fluxes of CO and of another line, which is N2H+. Why is this method used? Without going into chemistry details, is because we expect N2H+ to anti-correlate with the CO abundance in disks. That's because N2 and CO compete for the H3+ ion in chemical reaction in the gas phase in disks. And because CO gas destroys N2H+. So the more CO you have, the less N2H+ you have in disks. So if you have this N2H+ flux and CO flux, you can use them to break the degeneracy of the CO abundance in disk and try to get a gas mass. So we did that for the exoALMA sample. With a follow-up program, we got the N2H+ and C18O fluxes of almost all of the sample. And we measured the disk mass with the standard flux methodology and compared it against the dynamical masses that we measured from the rotation curves. So you're seeing here in the plot the log of the ratio of the mass estimated from the fluxes and the masses estimated dynamically. And you can see that they're pretty decent. I would say the differences of the order of factor of 2 for most of them. And that's the first time that these flux-based gas masses in this are benchmarked with a completely complementary method, which are rotation curves. And what this is telling us is that at least for the fairly narrow stellar mass range we have in our sample, we seem to say that this is that this method of using fluxes works, which is great because then we can extend it to sample for which we are not able to compute dynamical masses for. So let me go here. I skip this. What about the 2D velocity structure? That's the other part of the talk. I will go very fast. So here I'm showing the velocity, the centroid map of, in this case, is 13 CO for all 15 sources. And if we take the same disks and we compute the residuals, in this case for 12 CO, these are the residuals we get. What can you see here? I'll get back to clear like spiral structure. You see in some objects, but in some of them, we do have some systematical effects where you get this weird quadruple moment in these inner regions, especially for inclined sources. We'll not get into detail, but we are still working on a way to get rid of these systematics, which we understand why it's happening. So what can we say from these 2D maps in like giving some key results very quickly? The first one is that we compared the residuals we get against synthetic observations of instabilities that may be occurring in disks, in particular VSI, vertical shear instability. Then I have magnetorotational instability and gravitational instability, and all of them have a different power spectrum of the velocity residuals. And at the moment, we do not see any clear signature of this kind of residuals in the data. Why is that? Possibly because they're not operating as much as we thought they could. But second, keep in mind that the systematics we have yet in the residuals may be hindering our ability to see them. But what about planet-disk interactions? We do expect planets to leave a mark in these disks, for example, by launching Lindblad spirals, potentially buoyancy spirals, maybe having circumplanetary disks. And in terms of the kinematics, we know from previous work that there are two main ways, or actually three main ways, to try to see these planets indirectly in printing in the kinematical pattern of disks. The first one is that as the planet launches these Lindblad spirals, we expect to see a red-blue, what we call Doppler flip in the data. And then in a few cases, we expect to see a distorted channel maps. This is what in the community they're called kinks. And in some cases, you expect to see emission associated with a protoplanet that in this model would be here. So what do we see in the data about this? Let's keep this one. These are, for example, 4 disks for which what's pretty clear is that we have clear spiral structure in them. In particular, this one here, which is a famous disk, HD135344b, and this one on the right-hand side. These plots, and we see the spirals both in 12 CO and 13 CO. These disks are extremely dynamic. They're also the most asymmetric in continuum emission, not surprisingly. And we see the spirals both in the velocity residuals, but also in the peak brightness temperature residuals, at least in a few cases. But not only, also in the line width residual. So if we model the line width as azimutally symmetric, we remove it, we still see the spirals in the residuals. Let's have a better look at one of them, this MWC758. You see this beautiful spiral. And you see the spiral also in these line width residuals. So line width is enhanced in a spiral-like pattern. Let's look at this in the polar coordinates. Pardon me. So on the top left here, you have the line width residuals, and here the spiral is very clear. Here we have the velocity residuals, and again, you see the spiral-like pattern, which I'm repeating here. But here in the top right part of the plot, of the slides, I'm plotting the gradient of the velocity residuals. Okay, so this is the module of the gradient of this polar map here, which are the velocity residuals. And if I overlay the gradient with the line width residuals, they perfectly overlay. What this is telling us is that in the velocity, the gradient of the residuals in the velocity maps, which are actually what you expect to be tracing, for example, the Lindblad spiral. I'm not saying this is a Lindblad spiral, But for example, what would be tracing a Lindblad spiral matches the enhanced, for example, density that you could be tracing by an enhanced line width. And so this seems to work. There is a lot more to be understood, but we think we are at the point where we can characterize spiral structure in this with this level of accuracy. But these papers are still, there's still quite some work to be done before they'll be submitted. Okay. I'll go here. I'm skipping this last slide. Okay, so what are we doing then? Are we in the same data? The spirals per se don't tell us, I mean, if you forward model them, you can try to infer where the planet may be if you assume that the planets are causing the spirals. But what we're also doing is we're trying to use statistically robust methods to identify localized clustered residual in a space velocity space. So in this phase space, to try to identify peaks or clustered of data points that hydrodynamical simulations tell us is where we would expect a planet to be. And we are applying this to the whole sample. There are a couple of promising candidates, but we're still working on it. But I decided to show it anyway, because I'm sure I would have gotten questions otherwise. What we're doing at the same time is to try to find these planets with follow-up observations with JWST, in particular with near iconographic observations, and from the ground with the new VLT Ares imager in L band at 3.8 micron. Why do we want to do this? Well, because we know that the magnitude of the velocity perturbation scales linearly with the mass of the planet, at least in the linear region. So if we were able to detect a planet and measure the magnitude of the velocity displacement at that specific location, and we did have a planet luminosity, we would be able to distinguish between very hot star models and very cold star models. So we would be able to construct a mass luminosity relationship of protoplanets, so that this is the very long-term goal. We have tried to start to do it. For example, that's a JWST, that's a cycle 1 still program, because it took a long time to understand the data that I'm leading, for which we went to look for one of these blobs, these circumplanetary disk candidate that we see from kinematics, from gas line, from ALMA, to try to see if we could detect the infrared counterpart of this putative planet. And what happened is that we do not have a detection at 4.1 micron. This is a near-cam imaging. This was without coronagraph, because it was cycle 1. We still didn't know the best practices. So what is going on? What may be happening is that, well, forward modeling of kinematics may be overestimating planet masses. We would have expected to see this planet. The second possibility is that radiative reprocessing of circumplanetary material is shifting the SED of the planet plus CPD to longer wavelengths. So actually we should go to 10, 20 micron to see these protoplanets. That's why we're trying with MIRI. And that the other possibility is that these massive planets are actually born colder than we thought. And the final possibility, unfortunately, I think we have to list it, is that everything I said about the dynamics being tracing planet-disk interaction is actually tracing another physical mechanism that we still have to identify. I think that's still an open possibility that we need to consider. So I want to go towards the conclusion, to the concluding slide. So I'll skip PDF 70 and I'll go here to my last 2 slides. Because I'm also trying to think about the future of what the field will be on, short and very long term. So what's very important is that we do have a mismatch in the population of the protoplanets, either via kinematics or by forward modeling substructures in continuum observations. And the planet population we have access to from radial velocity or transit surveys of exoplanets. And at some point, we will want to get close in the parameter space. But not only is that in the next years, we expect to have a lot of fairly massive planets being detected in within, let's say, 10 AU range, for example, from Roman using microlensing or from Gaia using astrometric measurements, So how can we bridge the gap in terms of facilities? And I think we have three opportunities here. The first one that is coming fairly fast, it's the ELT that will give us exquisite angular resolution, in particular with the METIS instruments, I mean, also with Mikado, but for the L and M bands, we will have METIS, which will be a fantastic way to try to hunt for these protoplanets, but not only that, to try to do these kinematical studies using fundamental raw vibrational CO lines at 4.7 micron. So we'll be able to witness the formation of a Jupiter-like planet at 10-ish AU. We have synthetic observations that show that it will be possible with METIS. And that's happening soon. It's in 5-ish, 6-ish years from now. The second new instrument, thinking longer term, is definitely the NGVLA, hoping all the funding will come from US Congress. In particular, the high frequency part, so the 3 millimeter wavelength, will be fantastic in probing kind of solar system scales or Jupiter kind of scale, formation scales for systems that are analog to our own solar system. This is like a Jupiter mass planet at 5 AU. How we would image that in a protoplanetary disk. I think that's fantastic. You also see the Lagrangian points here. But there is a third instrument which is not discussed a lot, which is the future of ALMA. So ALMA now is undergoing a significant upgrade in its correlator in enhancing their correlated bandwidth, which is called wideband sensitivity upgrade. But it's not clear what will happen after the 2040s. So as a community, we are starting to brainstorm and discuss about a major upgrade, effectively, a completely new facility, new interferometer, millimeter wavelengths, which would upgrade or replace ALMA after the 2040s. So I'm currently kind of leading these efforts. So if it's something that you're interested in, please come talk to me in front of a glass of wine. So to conclude, since I went over time, what are we seeing from this data? First of all, is that disks are extremely structured in their kinematical pattern. We have a new way to characterize the pressure modulations in disks that do match with the annular structure in dust. And we have observational evidence for it. We have a new methodology of estimating disk masses, which seems to work very well when we compare it against flux-based disk masses. And I think we have evidence, or at least indications of planet-disk interactions ongoing in this that now we can study in detail. And I think for the future is really this millimeter infrared synergy. So comparing the kinematics we see in the gas with the direct detection of protoplanets that will make the field make a huge step forward in understanding how these protoplanets are born while they interact with their natal environment. And with this, I'll stop and take any question you may have. Thank you.